Hi everybody again. So I continue with my examples from section 5.3. Just want to make a correction. That last one I just finished in the previous video was example 2, number 1 from page 253. I think I wrote example 3, but it was example 2, number 1. Now we're going to example 3, which is on page 254. So now we're doing the applied problems. Now that we know how to, given an area, find the z-score, we're going to apply this. So if you recall, we have a z-score formula that converts a data value x into a z-score. X minus mu, the population mean, over the standard deviation sigma. But sometimes what we want, we know z, the z-score, because we've got an area, we've looked it up. We know mu, the population mean, we know the standard deviation. What we want is x. So let's just make our algebra a little easier, and we're going to resolve this formula, x equals mu plus z times sigma. And this formula is on the formulas page, and I should have said that in the last video. You need to have the formulas page that I posted in weeks 11, 12, 13 for chapters 5, 6, and 7. You need to have your z-scores. Really, it's best if you can print them out, or you have the one in the book at the end of the book, or if you have the actual book, it's kind of on a cardboard, the z-scores. But if you can print them out, I know that's kind of hard these days, but if you can print them out, that would be helpful. So we're going to use this formula now. Given a z-score, find a data value x that goes with it. So we're going to go to example 3 on page 254. And this says, a veterinarian records the weights of cats treated at a clinic. The weights are normally distributed, so we can apply all of our normal distributions, formulas, charts, graphs, all that. The mean is 9 pounds, mean weight of the cat, and a standard deviation of 2 pounds. So that's mu and sigma. Find the weight x corresponding to each z-score, interpret the results. So number 1, if we've got a z-score of 1.96, that means that this cat, let's call the cat Fluffy, is 1.96 standard deviations above the mean weight. That means Fluffy maybe needs to go on a diet, right? Fluffy's a little chubby. And so almost 2 standard deviations. That's almost unusually big for a cat, big boned for a cat. So what we want to do is find out how much does Fluffy weigh, that cat, if that cat is 1.96 standard deviations above the mean. So we're just going to put everything into this formula. So I'm going to take x equals mu 9 plus z was given 1.96 times sigma 2. So order of operations, you always multiply before you add. So 1.96 times 2. You can probably put this whole thing into your calculator just like this. It'll probably do it in the right order for you anyway. But technically multiplying first, it looks like Fluffy, our cat, weighs 12.92 pounds. Now, of course, there are different kinds of cats and all of that, but anyway, we'll just go with that. So, example 3, number 2. Example 3, number 2 says, what if the z-score for our cat is negative 0.44? That means this cat is 0.44 standard deviations below the mean in terms of weight. So, a little less than 9 pounds, because the mean is 9. Not super skinny for this cat, not too malnourished, but below the mean weight. So again, how much does this cat weigh? So we'll call this cat slim. So what we're going to do is we're going to put this into the x formula up here. We're going to put in our information. So x equals mu, remember, was 9, plus z, negative 0.44, times sigma was given as 2. So multiplying first, 9 plus negative 0.88, which means Slim, our cat, let me move that up so you can see that. Slim, our cat, must weigh 8.12 pounds, a little less than the mean weight. And then our third question for example 3 says, what if our z-score for this cat is 0? That means this cat is 0 standard deviations from the mean in terms of weight. So, hey, the cat must be the mean weight, right? If there's 0 standard deviations from the mean, the cat must weigh 9 pounds. But let's prove it with the formula. So we take x equals, again, this x formula here we're using, which is on your formulas page. X equals mu 9 plus z is 0 times sigma 2. So 9 plus 0. Sure enough, that cat, we'll just call that regular cat, weighs 9 pounds. If the cat is 0 standard deviations from the mean weight, that means the cat is the mean weight of 9 pounds. So now going to example number 4, which is on page 255, more applied data here. So going to example 4, page 255. I'm going to put it all together here. So this one says scores, and this is real data, scores for the California Peace Officer Standards and Training Test are normally distributed, so we can apply all of our formulas and charts and graphs and all of that, with a mean of 50, so that's mu, and a standard deviation of 10, that's sigma. An agency will only hire applicants with scores in the top 10%. So when they give you a percent, they're giving you area, and something has to tell you where you're going to shade. Here it says the top or highest scoring 10%. What is the lowest score an applicant can earn and still be eligible to be hired by the agency? So let's draw the picture, because that always shows us a lot about how we do this problem. So this is applied data. So the mean is no longer 0, the mean is 50. The top 10% of people who take this test, the highest scoring 10% would be over here in the right tail. It's the highest scoring 10%. So we want the z-score, but then we want to work our way back to what's the test score that puts somebody in the top 10% for this particular test. So this is the area to the right, but remember we always need the area to the left. That's what we need to look up. So what we have to do is take our total area, 100%, minus that 10% to get 90% to the left, or 0.9000. Again, if you go back and look at the earlier video, we always put 4 decimal places on our area because that's how it shows up in our table. So we're on the positive z side here, and we're looking for the area to the left, not the area to the right, which is 0.9000, and we actually just looked this up when we did the 90th percentile, you might recall, in the earlier example 2. So the first 0.90 in the table is here at 0.9015. That's too big. We want 0.9000. We look to the left, 0.8997. That's too small. We want 0.9000. Is one closer? Yes, this one's a lot closer. This is 3 10,000ths away, whereas this is 15 10,000ths away. Again, you can pick the bigger number in terms of, might be greater than the area you want, but it needs to be the closest. So this one's the closest. So the z-score that goes with an area of 0.8997, which is the closest to 0.9000 in the table, is 1.28. So that's the z-score we're going to use, 1.28. Now we are not done, because we need to find what's the data value, x. What does somebody score on that test to put them in the top 10%? So again, we've got this formula, mu plus z times sigma, that we just talked about from example number 3. So now we have the information, mu 50 plus z we just found was 1.28 times sigma was given as 10 at the beginning of the problem. Multiply first. 50 plus, this gives you 12.8, which is going to give you about 62.8. So to be scoring in the top 10% on that test, somebody would need to score about 62.8 or above. Now, maybe you can't score 62.8 on a test. Maybe it would have to be 63, but they didn't tell us that. So we'll just keep it at 62.8. Anybody who scores that or above is eligible to be hired for, it sounds like the California Highway Patrol, probably. All right, so last example to look at here is example 5 on page 256. And this one, again, is real data. It says in a randomly selected sample of women aged 20 to 34, the mean total cholesterol level is 179 milligrams per deciliter, with a standard deviation of 38.9 milligrams per deciliter. So that's our mu, population mean, and standard deviation sigma. Assume total cholesterol levels are normally distributed, so we can apply all of our normal distributions, graphs, charts, tables, drawings, all of that. And so what we're going to put in the middle is our population mean mu of 179. That'd be really healthy, 38.9. And that's our population mean. And now it says Find the highest total cholesterol level women in this age group, age 20 to 34, can have and still be in the bottom 1% for cholesterol. Is that a good thing to be in the bottom 1%? Yeah, that means you're super healthy, right? The vegans or something probably. So the bottom lowest 1%, that would be over here. It's only 1%. That's way less than 50%. So we want to find Z and then work our way back to what's the cholesterol level that puts someone in the bottom lowest 1%. Again, we're going to look up that area in the table. So we got to convert it from a percent to a decimal, move 2 places to the left is 0.01. I'm going to add 2 zeros because, again, in our table, area has 4 decimal places. So where am I going to find that? I'm on the negative Z side to find that really small area. So I'm looking in the Z table for 0.0100. I'm hoping for an exact match. But if it's not an exact match, I want to find the closest. So I'm in row negative 2.3 as the first 0.01 something. 0.0102, which is a little bigger than we want. It's 2 10,000ths bigger than 0.0100. So look to the left. 0.0099 is a little smaller than we want. But it's only 1 10,000th smaller than 0.0100. And you can always subtract on your calculator to see the difference. So this one's closer. Again, you might pick the bigger number. It's just whatever's closest to what you're looking for. Happens to be this one. So I'm using negative 2.3 and look up and 300ths. So that's the Z-score, negative 2.33. Now I am not done because what I want to do is find what's the cholesterol number for that person. So we have to go to the X formula. X equals mu plus Z times sigma. So we're going to take X equals mu, 179, plus Z we just found was negative 2.33 times sigma, 38.9. So 179 plus, using our friend the calculator to multiply that out, negative 2.33 times 38.9 gives me negative 90.637. Don't lose your negative signs along the way. Plus 179 is going to give me my answer of 88.363. That's a really low cholesterol level, right? And they'll tell you in my math lab, my stat lab, how they want you to round. So somebody who has a total cholesterol of 88.36 with 88.363 or lower is in the bottom 1% for cholesterol. It's definitely a super healthy person. So there we go. Those are the examples from 5.3. Hope you found that helpful.